Introductory Statistics Module 8, Sampling Distributions. Section 8.1, Distribution of the Sample Mean. We'll look at these two objectives in this section. Statistics, such as X bar, are random variables since their value varies from sample to sample. As such, they have probability distributions associated with them. In this chapter, we focus on the shape, center, and spread of statistics, such as X bar. The sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. The sampling distribution of the sample mean, X bar, is the probability distribution of all possible values of the random variable X bar computed from a sample of size n from a population with a mean of mu and a standard deviation of sigma. So to illustrate sampling distributions, step 1 is to obtain a simple random sample of size n. Step 2, we want to compute the sample mean. And then step 3, assuming we are sampling from a finite population, repeat steps 1 and 2 until all simple random samples of size n have been obtained. So objective 1, describe the distribution of the sample mean for a normal population. Example 1, the weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and standard deviation of 0.02 grams. We want to approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n equal 5 from this population. The data on the following slide represent the sample means for the 200 simple random samples of size n equal 5. So for example, the first sample of n equal 5 had the following data, and we see these 5 values listed here. X bar is equal to 2.479 for this sample, and we found it by adding those 5 values together and then dividing by 5. So the values we see on the next slide represent these sample means, or the X bar. And here we see all 200 of them. If we took the mean of our means, so the mean of those 200 values, we would get 2.46, which is the same as the mean of the population. The standard deviation of the sample means is 0.0086, which is smaller than the standard deviation of the population. The next slide shows the histogram of the sample means. Notice that the shape of the distribution of our sample means is approximately normal. So what role then does n, or the sample size, play in the standard deviation of the distribution of the sample mean? As the size of the sample increases, the standard deviation of the distribution of the sample mean decreases. So let's look at this example again and look at the impact of the sample size on our sampling variability. We want to approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n equal 20 this time from the population of weights of pennies minted after 1982. And remember that our population mean value was 2.46 and our population standard deviation value was 0.02 grams. So here we see our picture. Notice that the mean of the 200 sample means for n equal 20 is still 2.46, but the standard deviation is now 0.0045. It was 0.0086 for n equal 5, so it's even smaller now. So as our sample size increased, the standard deviation decreased. As expected, there is less variability in the distribution of the sample mean with n equal 20 than with n equal 5. So let's look at the mean and standard deviation of the sampling distribution of x bar. Suppose that a simple random sample of size n is drawn from a large population with mean mu and standard deviation sigma. The sampling distribution of x bar will have a mean mu sub x bar, which is equal to the mean of the population. And our standard deviation for our means, sigma with a subscript of x bar, is equal to the original population standard deviation divided by the square root of n, where n is our sample size. The standard deviation of the sampling distribution of x bar is called the standard error of the mean and is denoted by sigma with a subscript of x bar. Let's look at the shape of the sampling distribution of x bar if x is normal. If a random variable x is normally distributed, then the distribution of the sample mean x bar is also normally distributed. So let's continue our example and we'll look at example 3, describing the distribution of the sample mean. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. What is the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams? So let's draw a picture. We draw our curve and we put our original mean, which is 2.46, in the middle. 2.465 will be above that. And when we want to find a sample mean of at least that, that means that's that or more, so we'll shade to the right of it. So we want to find the probability that our sample mean is greater than or equal to 2.465. So the mean of x bar, remember, is equal to the original mean, which was 2.46. But we need to compute the standard deviation of x bar. So we take the original standard deviation and divide by the square root of n, or our sample size. So we have then 0.02 divided by the square root of 10, since our sample size was size 10. And we get a value of 0.0063. So we want to convert this to a z-value. So we take 2.465 minus 2.46 divided by our new standard deviation value, which was 0.0063. And we get a value of 0.79. So we want to find the probability that z is greater than or equal to 0.79. So we can look at our table, and we want to look at 0.7 and 9, and we get this value here. So this will be equal to 1 minus the value from the table when we looked at 0.79, which is 0.7852. So we'll get a value of 0.2148. Objective 2. We want to describe the distribution of the sample mean for a non-normal population. So we'll continue our example and look at example 4, sampling from a population that is not normal. The following table and histogram give the probability distribution for rolling a fair die. Remember that the faces of a die are the numbers 1 through 6, and we have a 1 out of 6 chance of getting each one of those. We can find the mean to be 3.5 and the standard deviation to be 1.708. And here we see a graph where all the bars are the same height since they all have the same frequency. So we can tell that this population distribution is not normal. Now let's estimate the sampling distribution of x bar by obtaining 200 simple random samples of size n equal 4 and calculating the sample mean for each of the 200 samples. We want to repeat for n equal 10 and n equal 30. So histograms of the sampling distribution of the sample mean for each sample size are given on the next slide. This histogram graphs our 200 sample means for a sample size of n equal 4. And this one is for a sample size of n equal 10. And here is our picture for n equal 30. Notice that the mean of the sampling distribution is equal to the mean of the parent population, and the standard deviation of the sampling distribution of the sample mean is sigma over the square root of n, regardless of the sample size. Also, we have the central limit theorem. The shape of the distribution of the sample mean becomes approximately normal as the sample size n increases, regardless of the shape of the population. So let's use the central limit theorem in this example. Suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. If a random sample of n equal 35 oil changes is selected, describe the sampling distribution of the sample mean. We can say that x bar is approximately normally distributed with a mean equal to the original one, 11.4, and a standard deviation will be equal to the original standard deviation, 3.2, divided by the square root of our sample size, which was 35, and we get a value of the standard deviation for x bar as 0.5409. If a random sample of n equal 35 oil changes is selected, what is the probability the mean oil change time is less than 11 minutes? So we'll use our mean and standard deviation in our z formula. So we take 11 minus the mean divided by the standard deviation we found above. We get a value of negative 0.74, and since we're looking at less than 11 minutes, we're looking to the area to the left, so we can simply look it up in the table and we'll get 0.23 for our probability.